Yeah, hello everybody to our 25th webinar in the POP2 project. Today we have Jesús Labarta with us, who will talk about 6.5 years of POP CoE, what remains. For those who don't know, basically the POP project, the second phase ended in May 22. There was a first phase which started in October 2015. And so we had like 2 project phases on a total of over 6 years to work on POP. And this webinar, we want you to kind of talk about the impacts we have, give you a summary what was going on and potential outlook in the future. So for those who don't know Jesús, he is the director of the Computer Science Department of Barcelona Supercomputing Center. But of course, he's also the coordinator of the POP project. In his research, he was working on task-based parallelism. So he was behind the development of OmpSs, the task model developed in Barcelona, but also his group was very influential on the task-based execution in the OpenMP standard. And then currently he's also working on the EPI project on accelerators for exascale computers and many, many other things. The last thing I want to mention is in 2017, he received the Ken Kennedy Award, which is, and I think he was the first non-US researchers to get this award. So we have a very excellent speaker today. And thank you, Jesús, for taking the time to talk about this topic for us, and I give the floor to you now.
Okay, hello, thank you, Bern. Thank you for the introduction and for the title, which you suggested to give this kind of overall view of what the POP project has been. And a title that invites you to look backwards and into the past. And the good thing when you can look really backwards into the past is probably you have many things to say, but probably it would be nice to see whether you can summarize your learnings under certain statements. And this is my kind of disclaimer. I'll try to say some things which are probably personal opinions, personal feelings and thoughts, and I might be very insisting, but kind of giving a personal view of what the project has been. And to start with, a little bit the kind of activities, and in a sense, it was a kind of peculiar project because it was not a really or mainly development project, but it was a service project, a project where people, be it application developers or be it just users, not even having developed the application, could apply to this questionnaire page here, and they would be assigned an analyst to work with them on the analysis of their applications. And the first thing was in the flow, in the process, was to obtain data. Of course, the possibility of doing it at the customer premises and by the customer itself with the support of POP experts to install the tools, maybe, or done at the POP expert premises. But the idea is to try and get data which is as representative as relevant for an interesting use case for the customer, which was then analyzed by the expert in the team. And this is probably the major effort, the major area where we have been doing developments, both in the methodology as well as the actual assessments and actual analysis of this application. The insight or the observations made by this analysis were provided as a report to the customer, which then could probably try to, at their pace, try to implement and to deploy them in their actual code, which would give opportunities for next follow-on audits and kind of closing the loop and making the possibility of having an external view, which helps them do the work, but kind of gives them advice on how to proceed. We had also other kind of services, like the proof of concepts, where essentially we would implement in part of the user level code, implement some of the approaches of how to address the issues identified in the assessments. These were the kind of services, and when I say it's kind of not a standard project, is because it was giving an external view, an external perception of what was happening with the application to users and developers. What will remain, this has been, as Bernd said, this has been two projects, two phases. What will remain? And if you ask me, the most important thing I think that we have been trying to push forward is the mindset. It's a way of looking at performance analysis. It's a way where we insist that performance analysis has to be part of the whole development cycle, and a way of looking at it beyond just the typical profiles, more into direction of really measuring and characterizing efficiency and working with real models of that behavior, and looking at fundamentals rather. Of course, you also have to look at syntax also, because you have to refactor the code or to improve the code, but it's looking at fundamental metrics, fundamental characteristics that describe the parallel aspects of the program. And there's another thing which I consider important was to go beyond just a superficial analysis of very, very generic kind of descriptions and try to go deep into the analysis. And there's this feeling that really when you acquire data from a program to do an analysis, there's a lot of data which very often is just summarized in very simplistic way. So the idea beyond first order moments is to go and do more detailed analytics and extract more detailed insight. But this is kind of a generic perception of what will remain. I think if you want to really have a look at it, I think the dissemination work package did a very nice job in terms of producing a web page which has a repository of a lot of materials, has blogs about the different analysis or events handled, has a lot of material about training, about success stories, and really the details of the studies that we have been doing. So we have also a co-design resources section in there, which you can look, where you will be identifying, seeing how some of the identified potential problems, how can they be addressed, and in some cases by looking at the code, but in some cases with input or even resources like codes, mock-up codes for microarchitectural developments. I think this material is pretty nicely available. You can really have a look at it at the details. So what I will be doing now is mostly kind of a generic description of the overall structure of the project and the overall perception from my point of view. And I will start by saying that one of the things that I think we'll have, and I have seen, is a certain feeling of belonging to the project, the feeling of having learned in the project by the different people. Actually, there's people who were analysts in the project who actually left their companies or institutions, are now working at other institutions, at Intel or at other companies, and when you talk to them, they're happy that of what the project did and the learning that meant for all of us. And the second thing where I think we had a good appreciation by customers. One other of these peculiar characteristics of the project is that we had a task which had to do with a customer advocacy. We're trying to send questionnaires to the users to find out what was good, had been good, what had been not so good, what was their perception about the service. And I do believe, and the outcome of these questionnaires is kind of that a large majority of the customers really appreciated this external view from an observer. Is not a competitor. We are not experts on the field. We are not going to work on those codes. It's just an external view, which sometimes lets people kind of gives people an awareness or a quantitative kind of estimation of the importance of the different behaviors, which very often, probably because of their involvement in the day-to-day developments, they have not had a lot of time to look at. So I will insist you that you look at the web page and navigate. But till then, just a little bit of summary of the number of studies and services. And in each project, we have done more than 150 studies and assessments. So we have been exposed to a large number of codes and proof of concepts, these services. And it has been a thing which has been, majority of them have been for academics, but we are proud that we have also gone more than 20% of our services were to industries. I've tried to put here a little bit of a description here saying that the activities were kind of transversal across domains. Engineering probably is the one that has more services, but there's a whole bunch of domains that whose codes we have been looking at or we have been exposed to. In terms of programming models, well, there's a dominating MPI and hybrid. MPI mostly MPI plus OpenMP, but there are other MPI plus CUDA or MPI, so accelerator models, or just OpenMP or OpenMP plus CUDA. In terms of languages, mostly C++ and Fortran. Also, some of them combined with Python. We have seen over the years, we have seen an increase in the use of Python. But still C++ and still Fortran are very, very important. And in terms of scales, I have a little bit here indications of the scales, how people was using or is using in production those codes, what were the scales that we were analyzing, and what were the scales the users were feeling comfortable with. So you get a feeling of the range of scales that have been analyzed with for most of these codes. Other thing that I consider has been important is our commitment and involvement and collaboration with the EuroHPC community. So we have been doing a large number of services for other centers of excellence, which were domain specific on a given application domain. We have done a lot of training activities with them, and joint training activities or ad hoc for specific uses. We have done a lot of dissemination. So I think this has been a good involvement from our side, a good motivation and commitment from our side towards these European efforts. On the other side, I think we have also gained a lot of co-design insight, which, as I said, is expressed in the web page, but also insight that we actually can use in other projects. As for example, I mean, Bert mentioned the EPI project. I mean, there's insight that we get from here, which we are trying to use in terms of steering the actual architectural designs in projects like this one, like EPI. So let's go to the overall focus of the project, which was performance analysis. And long time ago, I think I gave a conference at SIAM, invited by Maiharu. The title was Performance Analysis Still When an Art. Okay, and it's I think that's still or is still being an important consideration. It's too much of an art from the point of view there's not really a very clear or unified methodology or approach, like many different people tend to have or use different ways of doing it, which might be, you might like better or worse, but a little bit I had this feeling that it's too much of an art, or it was too much of an art, and a little bit the motivation of the project was kind of push a little bit more towards the use as science. And as science, I think some of the things that you need are really certainly tools and measurements and precise measurement tools. And it's kind of this feeling that in science, there are huge and enormous and extremely precise tools, where very common practice in computer science is to use different kind of tools, okay? It's a situation where typically see just an aggregated numbers and we try to speculate about the microscopic behavior. So it's a field where traditionally we have been kind of using computers to study other domain of sciences, but we have not really done a lot of analytics and a lot of models and a lot of precise measurements in our own system. So these tools is an important component. Models is a second very, very important component, and a methodology. So what I will try to do now is describe a little bit about the tools, models, and methodologies being used in POP. And in reality, POP integrated partners which had had a long tradition in performance analysis tools. We at BSc had a lot of tradition in trace-based tools. Jülich had a long tradition in profile tools and large-scale analysis. And in a sense, we have been using mostly these kind of tools, of course, with the support of other tools in the last phase of the project, for example, another vendor tool, but trying to use these tools in the analysis of the codes. As I said, as part of the methodology of the project, we have been developing a methodology, and the result is that we have extended the tools with components where we report the metrics. I will explain in a minute of the methodology. This has been integrated in Scalaska, has been integrated in Paraver. There was a kind of Jupyter Notes kind of framework around the Paraver tools to kind of directly produce the reports. But I think this is an important thing. This is kind of two kind of different tools and two kind of initially different philosophical approaches. We have been able to come out with a unified set of metrics that lets us look at the world, let's say, with the same language. And in a sense, this language is a top-down model of description of the performance. So this is going back to models. The second part is a description of the performance of an application with metrics, with components that are very, very abstract, have to do with fundamentals of parallel computing and not really with syntactic aspects or with domain-specific aspects. This is in a sense, is a transversal language across domains where a guy from life sciences can talk to a guy of mechanical engineering and can really share a common language and try to see if they have the same or different issues, but fundamental issues. So we have these kind of 6 basic fundamental metrics, which have to do with load balance, realization, and transfer to describe the parallel behavior aspect of the application, and IPC scaling, frequency scaling, and instruction scaling to look at the scalar part of the computations. It is very important to say that these are kind of descriptive parameters. Okay, I'm not going to go into the details now. You have the details again in the web page. You have previous webinars that have gone in detail throughout these metrics and how these metrics are computed. But the important thing, I think, is that the metrics themselves are a quantitative abstract description of the behavior, of the parallel behavior. And as I said before, then we have to go to causes. And the issue is that these causes can be many and can be coupled. And can be, so is this the point where really we need the very high precision capabilities of the analysis? At the very first level, you can just get a top-down view, which essentially helps you steer the search for the reasons and for the causes of the inefficiencies, and this search will actually prepare you to really address the refactoring in the right way, or in the understanding the fundamental reasons for the inefficiencies. If you understand the causes, of course, you can really address the causes. It is also possible to understand the causes by saying, okay, the cause is there, but I can addressing it there is going to be difficult, it's going to be expensive for me. I can compensate the symptom somewhere else. And so there are all of these possibilities that can be discussed based on the inner analysis, which I think is really totally necessary, of the inner of the identification of the causes. Before going to some example of the methodology, how those things can be done, just mention that we have actually been doing also extending the original model, which was essentially for MPI programs. We have been extending it to hybrid models, where we have actually developed 2 variants of the model, a kind of additive model and a multiplicative model. And in reality, where you can look at, if you can look at the efficiency of the application from a holistic point of view. So is load balance across all resources that I have well distributed or not? Do I have problems of transfer of data between my resources or not? In a holistic way, kind of the whole application, or you can look at it from a different perspective and look at it from the individual perspective of the individual components. Am I good at the MPI level but bad at the OpenMP level? I mean, kind of things that probably might, I mean, you might be interested in saying, do I have to hire an MPI expert or an OpenMP expert? So this kind of understanding is probably a useful, interesting, an interesting perception. And we have extended these things, and these basic models apply them also to more generic models, more hybrid models like MPI plus CUDA, or these kind of hybrid models which are also used. So till now was about the models. The idea is now to talk a little bit about practice and methods. And typically, a certain perception I had, which is this typical approach where you measure timing of your program with different core counts. You plot nice speed up curves or nice efficiency curves. And from here, we try to speculate, or we have to say, oh yes, I have this thing because of communication being a bottleneck, or because of cache misses, or because, so a certain belief that we, as I said before, that we try to look from this very high level, very aggregated, very lacking actually the structural detail of the internal application. We try to extrapolate, and I think this is good to have. It's certainly a first step to have. But at the very end, a time or a profile is probably not not necessarily the thing to blame. The example I use here is a profile telling you that you spend a lot of time in MPI. Does not necessarily mean that you have to blame your vendor or your MPI provider. Maybe the problem is a different thing. So just looking at the profile, maybe the problem is just load balancing, or maybe just is the order of your computations that you enforce. So I think we need to go to this more fine-grained type, or more, and actually even more fundamental type of analysis. So what we propose is kind of a journey with these kind of phases, which we say identify the structure of the application, a very important first step. This is about curiosity. This is about, I mean, and typically we are analysts, that we are not experts on the application. We see it for the first time. We don't know, and the idea is having curiosity about how things are. And this is a very important thing to have in art and in science also. The second thing is, having done this analysis, to select, now I'm going to do my analysis on this part. I mean, the typical example I use here is, I mean, had you been to Siberia and taken out from the permafrost a mammoth and you want to sequence it, you don't put the whole mammoth in the sequencer, right? You try to find a good part of the tissue which is not perturbed nor corrupted, and so you really need to select what you really want to analyze with the best guarantees that it is a real good unperturbed, or as unperturbed as possible data. Finally, then on that data, you apply the metrics that we have been describing, and this gives you kind of indication to steer which are the fundamental problems that that you should be digging down more, and then you should be doing a detailed analysis. I will comment a little bit on this in order to draw your conclusions. So let me go a little bit through the different phases, and in terms of structure, this is the kind of things, and I will be doing a little this with mostly with Parallel, because it's the tool I've been mostly using. But what I'm trying to say is that the process is a whole process that can be applied with Parallel, can be applied with Scalaska, or could be applied with any other tool that you might have, as long as you kind of support or measure the efficiency models, which, by the way, is not complicated. So curiosity is the driver for the structure part. I mean, you have to try and see, and here these are timelines. Here we have 380 rows. The color represents, according to this scale, how long is the computation. So you have short computations, longer computations, short again. The top view here is about the MPI calls being done by each of these 384 cores a long time. And with this view, sometimes with the help of some others, you may identify phases, you may identify iterative structures. With these views, maybe a little bit of your input from your customer, or the kind of indications. Oh no, this is a solver, that the system that is applying a solver iteratively, so you really see and identify the regions. The regions, essentially the regions that you would put into the sequencer. So what is, for example, 2 iterations if the algorithm shows iterative structure, which needs not always be the case. There are also some cases where the iterative structure is not only in time, but also on space. So this is something which is very, very, very algorithmic dependent. Typically, time iterative structures are very frequent, of course. The other thing that you can do during this kind of observation phase of a structure is kind of look at perturbations, and you can really identify regions in your data which are somewhat perturbed. And this helps you obtain kind of the samples that you will put in the sequencer, which as clean as possible. So in reality, once you have identified as clean as possible regions, you can analyze them with more detail, just still curiosity and looking at different views like how long are the messages, or looking at this view, which are the MPI calls being used, or how long is the computation, and you can really do this, obtain the same samples for different core counts, and you can see if the structure is something that really repeats or is maintained with the scale or not. In many cases, the structure kind of preserves with the scale, but there are cases where that does not happen. Once you have your region of analysis, you can do the typical scaling, of course, as you did typically for the whole application or with timers in the source code. You can really do for those regions of analysis, you can really do a typical time-based scaling model, which would give you a reference, but the immediate next step would be to build the efficiency model and really get a little bit of insight of which are the real causes or the real effects that are kind of making your performance degrade. From a global efficiency, all these numbers are initially between 0 and 100. Actually, the ones on the top are absolute efficiencies, so between 0 and 100. The ones at the bottom, having to do with the computation scalability, take as reference one of the cases, typically the smallest core count that is taken as reference, and the others are relative to that one. We do not enter in the algorithmic considerations whether you are doing a program with the best numerical algorithm. We are looking at the parallelization aspects of this algorithm. But these numbers tell you a little bit what are the things that you should be looking at and effects that happen. And actually, sometimes you see this is an example where there are effects that instruction scalability goes down pretty rapidly, which means there is should be somewhere replicated code. This case is executing more the instructions than this other one, even if this is a strong scaling problem. On the other side, here we have an example where, looks like for some reason, the IPC gets significantly better in this case than in the reference case. And both things can compensate each other. Still, computation scalability improves with scale. And this is not that typical situation, but it happens, it can happen. It will not stand forever if you keep increasing the scale, but it may happen. But the thing is, you have this efficiency model that can be used to steer your scaling metrics. What do you do once you identify which are the metrics that you should be looking most? You have to try to dig down into them. And here you need really the analysis capabilities and the deep analysis capabilities, and you really need to look at timelines. You really need to look at histograms. Histograms is something which is not that frequently looked at in a lot of performance analysis, and they are extremely important. And we have here histograms, which is kind of express a little bit the variability across different threads. Here you have the case where there is very little variability between these threads, but there is a lot of variability between these other threads. This is a histogram these are the kind of along this X dimension, we have the bins of the histograms. This is one of the things that you may want to load balance. You may want to look at communications. And one of the suggested and the most important things in terms of the communication analysis is really to compare the real behavior, what did happen on the run, compared to what would be an ideal behavior. What would have happened if communication had been instantaneous, zero latency, infinite bandwidth. And these comparisons of different of these configurations, and maybe you can compare it with a nominal network, they can actually give you a lot of insight about how much those transfer metrics that we identify are really transfer. Where do they happen? Do they happen equally on all parts of the application or not? And you can actually do more detailed what-if analysis and really see what the impacts of latencies and bandwidths are, and maybe see that, for example, on this part here, there's changing latency is not a big issue, but but change in this part here, but changing bandwidth is. Or at the end is kind of gaining insight of what are the fundamental sensitivities of your program to architectural parameters. The other part which is extremely important to look at is the scalar behavior of the programs, and looking at hardware counters, of course, that we capture with all our tools, and how those hardware counters evolve with scale. And well, this is an example of a hybrid run of a code which goes from 48 processes single-threaded to 18 threads. And you can look at the evolution as you increase the scale of different regions of the code. Here, every region of the code every color is one region of the code, and you see how the instructions go down. This is what you would expect as you increase the scale. The arrows go down everywhere, which means that the total number of instructions shrinks. This here is IPC. You see, everybody stays more or less as it is. There's one case which really shrinks IPC a lot, and really this actually shows things that a region of code which was not really relevant at the initial scales will end up being very relevant at large threaded scales, and actually points you to a specific region of code where you may have some issues with threading. Anyhow, the evolution of the scalar code behavior of whether the problem is because of cache misses, because of branches, or because all of this can be studied. What are the results, or what have been the results of these things? Okay, this is a kind of a little summary of for different studies. There are not all of them, but for different studies, we took the largest configuration that was analyzed, and we look at the metrics of that largest configuration, all of them, the serialization, the transfer metrics, or their aggregate, which is the communication, or their load balance, or their computation scaling. We look at each of these individual metrics for that case, and we arbitrarily said, okay, we consider a metric, an efficiency being bad if it is below 60%, being poor if it's below 75, good, fair if it's below 85, and good if it's below 100. And super would be super linear. And so we try to put here how many of those studies showed bad, poor, fair, good, or super linear. And you really see that at the very end, there is actually room for improvement. There is not the same, each case is a world in itself. So, and probably the other interesting thing for actual code developers is sometimes somebody comes thinking, oh, my problem is this one, and yes, that is part of a problem, but maybe you have other problems which are as important as that one. So these are very, very coupled effects that we kind of pinpoint. And really we see, I mean, transfer communication is an important issue in this case. Probably in this situation, probably I was actually a little bit more than load balance. There were more load cases with good load balance, but both of the fundamental problems have some really performance load causes some performance losses. And if you look at computation scaling, and these people is not really sometimes that much aware of the actual amount to which their instruction scaling or their IPC scaling is actually causing parts of the problem. Just to mention that we did also the proof of concept studies, where we kind of, mostly in cooperation with the customer, try to demonstrate on their code approaches to address some of the issues, some of the metrics that we have found not being very, very good. And of course, for every code, the analysis itself drives you in a possible different direction. But we have had cases where we have this kind of order of magnitude of the gains by, for example, rescheduling communications. Or here we have, well, you don't see, but there is also an important, significant reduction of the execution time. This is faster, and where what we achieve is by actually dynamically introducing dynamic load balance, we kind of avoid regions of time with not all the processes are computing. So these were studies that were done, and what was the result of those studies? Where did they take us in terms of results? In some of those where either the customer themselves or the POP partners did some analysis. What were the gains? And probably this is something that people often ask very much. How much did we gain? And I would like to say that you have a little bit of everything. You have a little bit of non-negligible gains, something, let's say 15, 20%. I have a couple of examples. These are actually taken from the success stories in the webpage. This I took a little bit better example. Sometimes it's only 15%, 20%, which, by the way, I think nobody would be unhappy if you were told that you are going to have a 15% increase in your salary. Okay, so I think they should be non-negligible. They're important. These things are important. There are other cases where the gain is twice, 2x or 5x or those order of magnitudes, and there are cases where you get to what would be impressive results. Okay, impressive results doesn't mean that we did miracles. We don't do miracles, but sometimes you kind of point or pinpoint a user to an area which probably because of being too much focused on its algorithmic work has not been really paying so much of an attention. So there are gains that in many cases is just by applying a better library because we identified issues with the library that was used, or issues by just, I don't know, switching from just a pure Python to I don't know, NumPy kind of thing. So it's some of these can be really extremely simple. The only thing what I think is the importance is that to identify them, is the pinpoint to really stress the customer in that direction. And there are some gains like being able to really scale to very, very, very large scales. So this wide range of gains, which is the result of those activities. The title of the call says about what remains, which is probably not only looking backwards, but also what remains to be done, what remains to be done in the future. And what I would like to say is that being mindset changes, this kind of a fundamental thing. So methodological aspects, one of the fundamental things. My comment is that in revolutions, be it the Industrial Revolution or the change from Middle Ages to Renaissance or other, I don't know, other revolutions, these changes really take some time. Sometimes it's years, sometimes it's decades. Well, some of them may take more or less. But I don't know, every single thing, I mean, how much did it take, even in computing, how much did it take for virtual memory from the first proposal to really being kind of moderately using everywhere? And all these things are decades. Many of the systems now, many of the hardware infrastructures that we have today is decades from 1 decade, from the moment you first proposed until the moment they really are considered a majority. So what we would like, we would certainly like to continue pushing and promoting this methodology. I think it has been a very good experience, and we have still a lot of opportunities to improve by sharing more tightly close the experiences between the different partners. We have done some sharing exercises, and the result has been very positive. We have also had, with this customer advocacy work package, we have also had requests from customers that they would appreciate to have more frequent interactions. Essentially, also with this training, the idea is to actually train them to be able to do a large part of it. Of course, as tool developers and as methodology developers, we will always try to run ahead and have better and more elaborated tools and methodologies, but we think it's important for people to convey this know-how to or these practices. And at the end, very often it's just a matter of best practices to the actual customers, and doing and developing more material, both training. We think it has been very useful, even for training internally within the consortium. The analysis, I think there's a large corpus of data there, material that everybody, I mean, this is useful for us, but this is useful for everybody. And you will see probably the differences that I mentioned between different analysis of partners, even if we have done this effort to try and homogenize. I think this would be important to keep going on those things and the possible co-design information that we have already mentioned a couple of times. Having said so, just to say this is something that we have done, I think, as a very collective effort with the 8 partners involved. Is so I say the blah 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 here, but really it's been a lot of collaboration. I think it's a very positive experience. And irrespective of whether we get it or not, the POP3, you know that you can contact us, and we will try to see if your case is an interesting one, or how can we continue these collaborations. Thank you very much.
Okay, thank you very much, Jesus, for this interesting summary about the achievements of POP. I also want to encourage everyone to check out the website where you find all the information and much more what is mentioned. Yeah, you find past webinars, you find our success stories, you find online training modules, you find lots of things. We have time for a few questions. You can type them in, and I'm happy then to relay them to Jesus and get them answered. And while you type something in, perhaps let me ask a quick question. So you mentioned there's like different things coming out of it, like the mindset, all the material, other things. So, but what do you think from personally? What is the most positive and most interesting thing you think came out of POP after these 6 years?
I mean, what I tried to say during the talk, I mean, the mindset is the most important thing. And personally, the experience is kind of just realizing how this effort of conveying a mindset, even through a team, which in this case is through the POP consortium itself, to the outer external community, how this is a really time-consuming effort, which on the other side is very kind of satisfactory to see when you have really made it to really get through and really be appreciated by a customer or by a colleague or by. So this is the most interesting thing for me. Technique is technique. I think it's very important to develop the tools, but those are technical things. Probably not the most important in life.
We actually have a question from Fabrizio Macluiani. I hope I pronounced that correctly. How do you envision to engage with quantum computers?
How do I envision to engage with quantum computing? You want my personal opinion? Well, it's my personal history, and I don't, as I said, I don't know the answers of other people. You know, when I got the Ken Kennedy Award, I asked one of the mentors, who actually one of the person who had supported me, was working in quantum computing, and I asked him, what should I do? Should I move, or should I go to quantum computing? And he told me, you are okay where you are. Don't move. You have a lot of things to do where you are. Keep going. Okay. So that was his message. Probably to me, Fabrizio, and you know, I mean, for my age, and probably believe, I think there's still a very challenging thing in trying to push this mindset activity.
Yeah, Fabrizio acknowledges that is a very tough question, and yeah. but I remember here at Jülich, where like our center people push for seeing the quantum computer as kind of an accelerator for traditional things, and so basically, yeah, like currently, as you offload now a kernel onto a GPU, you could envision that you have a specific optimization process where you envision it to offload it to the quantum computer, and then you would run into the same issues as we have with accelerators. Yeah, like we can analyze them and look at them. Basically, is it worth moving all the data over, wait for it and getting back, or would it be just faster? And
sure everybody's doing. You at Jülich are doing, BSc is also doing. So a lot of people is looking at that. My comment is, it's fun. It's a good thing. It's a good research area. It's a good research topic. But to get to the level of maturity, and still many things that we can do in the focus of analysis of POP, I think it will take some time.
Yeah. Okay. We also typically say in our training that first you do the correctness and then the tuning. Yeah, because nobody cares how fast you can compute the wrong answer. So again, I guess the quantum people probably I'm not an expert here. Perhaps I've said something totally wrong, but they need to make sure that they have all the errors under control and that they compute everything correctly. And then the next thing would be to make it faster.
And the noise and errors is a challenge thing.
Yeah. Okay. Seems to be we have no other questions, and so you answered all the questions people have. So thank you again, Jesus. This kind of closes the last webinar of POP, and for that it's the last kind of action for the POP project, which makes me a little bit sad. But thank you everyone for joining. As usual, every person registered will get a copy of the slides, but at some point they also will be, the recording and the slides will be also made available on the POP website as in the past. So thank you everyone again, and goodbye.